Okay, today we're going to talk about limits, and limits are essentially the basic question that you want to ask with a limit is, as x is approaching a particular value, what is the y value of that function approaching at the same time? So essentially, if we plug in 2 here, we're going to get 4 minus 4, which is 0. And on the bottom, we also get 0. Now, we will learn in just a little while that 0 over 0 is what is called an indeterminate form. It's not 0. So we actually don't know what 0 over 0 is because, not to get too technical, but this 0 could be much bigger than this 0 because we're dealing with limits. So we have to find another way to do it. The first way we're going to look at is what's called the graphical approach. And so we're going to ask the question, what happens when x equals 2? So we know from Algebra 2, if we wanted to graph this function, we would factor the top, and we would get x plus 2 and x minus 2. And then on the bottom, we already have an x minus 2. And so we can see here that the x minus 2's are going to cancel. And now we essentially are left with a new function. So we're now left with the limit as x approaches 2 of x plus 2. So we can see that the answer is simply 4, but let's go ahead and graph this. So x plus 2 is going to be a linear function shifted up 2 units. And we can see that there is a hole, so we'll say there's a hole located at x equals 2. We learned in Algebra 2 that anytime a factor on the top and bottom cancels, it's going to create a hole on the graph. And so there's a hole at 2. And to figure out the y-coordinate of the hole, all you do is simply take the x-coordinate and plug it into the existing function that you get after the factors have been canceled. So 2 plus 2 is 4. So there is a hole located at 2, 4. So let's go ahead and put that on our graph. 2, 4, hole. And once again, this is a linear function. So it's just going to be looking something like this, with a hole at 2, 4. And so now we're able to say, as x gets closer to 2, then the y value of this function is getting closer to 4. And that is the idea of a limit. You're simply asking, as x gets closer to a certain value, what is the y value getting closer to? Okay, here we have the second example here. And we want to also find the limit as x approaches 3 of f of x, and here we have what's called a piecewise function, which basically means that when x is less than 3, the function is going to resemble a parabola. And when x is greater than or equal to 3, the function is going to look like a linear function. So let's see if we can sketch both of these. So first thing you want to do with these problems is you want to plug in the point where the function splits into both functions to figure out the ordered pair. So if you plug in 3 into the parabola, we get 3 squared, which is 9 minus 4, which is 5. So this parabola is going to end at 3, 5. And if you take that same point and plug it into the linear function, 3 plus 2 is 5, we see that the linear function starts at 3, 5. So essentially, you can get where one function ends and one starts, which can tell you whether they connect or not. So we're going to go ahead and put the point 3, 5, 1, 2, 3, 2, 3, 4, 5, put that point on there. And now we will graph the parabola, which is a parabola shifted down 4 units. So it's going to look like this. And open circle. But the linear function has a slope of 1, all right, and it's going to close in that circle because it's a greater than or equal to, and so there's that. So as x approaches 3, we end up getting a y value of 5. So that's a very simple problem, and that is how you use the graphical method to determine what the limit is. Okay, now we want to talk about when a limit does not exist. And there are essentially 3 situations where you will say the limit dne does not exist. The first is when the y value, because we know f of x is the same as saying y, approaches a different number from the right side than it does from the left side. So an example of this may be, let's say we have a function that looks like this, and let's say it's some sort of piecewise function, something like that. And as, let's say this is the number 2. As x approaches 2 coming from the left, the y value is approaching, well, let's make up a number, let's say 1. But as you approach 2 from the right, the y value is approaching, let's say 4. Because the limit from the right does not equal the limit from the left, therefore you will say the limit as x approaches 2 of f of x does not exist. So that's the first reason. Second reason is if the y value goes to infinity as x is approaching a certain number. This normally happens at asymptotes. So if you have an asymptote, then as you get closer to that asymptote, the y value is going to be going up to infinity or down to negative infinity. And then the last situation is if the y value is oscillating between two fixed values as x approaches c. So let's just see if we can determine why each limit does not exist. So letter A, the limit as x approaches 3 of the absolute value of x minus 3 over x minus 3. When you plug in 3, you get 0 over 0. Well, let's just see what this function actually looks like. You can see that x minus 3, anything divided by itself is always going to be 1. And as long as x is bigger than 3, then you're going to have the exact same number on the top and bottom because the absolute value of the top is going to be positive and the bottom is going to be positive. So from, let's just say 3 on, you're going to have a constant function of 1. And you can plug in some numbers and prove that to yourself. And however, if you plug in a number smaller than 3, like let's say negative 2, or let's say 2. 2 minus 3 is negative 1, but the absolute value of negative 1 is 1. And 2 minus 3 is negative 1. And so a positive 1 over negative 1 is going to give you a negative 1. So for any number less than 3, it's going to be negative 1. Now what's the problem here? As you get closer to 3 from the left side, the limit is approaching negative 1. As you get closer to 3 from the right, the limit is approaching 1. So what you'll say here is the limit as x approaches 3 from the right, and that's how you denote it with the little plus sign, of f of x does not equal the limit as x approaches 3 from the left. Therefore, and that's what those 3 dots mean, so we put f of x here. Therefore, the limit as x approaches 3 in general of f of x does not exist. And so that would be the reason why this limit doesn't exist. Okay, example B, here we have the limit as x approaches 1 of this particular function. So let's just see if we can graph this. We know that anytime you have a dividing by 0 situation, that's going to create a vertical asymptote on your graph. So x cannot equal 1 because 1 minus 1 is 0, you'll be dividing by 0. So therefore, there's going to be a vertical asymptote at x equals 1. Now we can also figure out the horizontal asymptote by essentially taking the limit as x approaches infinity. So essentially we're asking the question, as x gets really, really, really big, what is the y value approaching? Well, if you put a really big number in here and then you square it, it's going to be even bigger. So 1 over a really huge number is approximately 0. So that means we're going to have y equals 0 as our horizontal asymptote. And we can see that this is going to have even symmetry because it's raised to an even power. And so therefore, we can say that this graph is going to look like this. Now, once again, at this point of the year, it's not critical that you know how to graph it. You can use a calculator and prove that to yourself. The point is that as x gets closer to 1, the y value is heading up to infinity either side of 1. So that's going to violate rule number 2. And so therefore, you will say it does not exist because of this reason right there. Okay, now let's talk about some special properties of limits. And so the first is the sum and difference rule. If you have a limit of two functions that are being added together or subtracted, then that's going to be equal to the limit of the first function, which we're calling L. So we're saying L is the limit as x approaches some number c of f of x, plus or minus the limit of the second function. So basically what this is saying is you can take one limit of two functions added together and you can break that up into two limits. That's all this is simply saying. Product rule works exactly the same. You can break this up into the limit of the first function times the limit of the second function. Any constant that's in front of a function, you can pull it outside of the limit and simply evaluate the limit of the function. And then when you get your answer, multiply that times whatever k is. Same thing works with the quotient rule. The limit of the top over the bottom, you can once again break that up into the limit of the top divided by the limit of the bottom. And once you get this number and divide it by that number, there is your limit. This is your power rule. We're not going to use that a whole lot, but essentially it says you can take the limit of f of x, which is raised to some power, and then what you can do is you can simply just evaluate what is the limit of f of x, and then once you get that limit, raise that to the power as well. Once again, we won't be using this that much. Let's see how these properties can be used in some problems ahead. Okay, let's say we have the limit as x approaches a of some random function f of x, and we're going to call that 2. And the limit as x approaches a of some g of x, we're going to call that 3. So part A is pretty simple. We can see that there is a constant in front of the function, so we can use what's called the constant multiple rule, which is what we stated in the table above. So we're going to rewrite this. We're going to bring the 5 out in front, so it's going to be 5 times the limit as x approaches a of g of x. And then we're going to recognize that the limit as x approaches a of g of x is 3. So 5 times 3 is 15. Pretty simple. Okay, part B, we're going to have to use a couple of different properties of limits. First, we see a quotient. We see a division. So we're going to break this up as the limit of the top function divided by, and this is as x approaches a. Oops, let me write that a little bit neater. As x approaches a. And then the limit as x approaches a for the bottom, g of x. Now, we notice that the limit as x approaches a, 6 plus f of x. Here is a sum of two functions. So we can use the sum rule. So limit as x approaches a of 6 plus the limit as x approaches a of f of x divided by the limit as x approaches a, I don't have room to write that, but you get the point, of g of x. Now, y equals 6 is just a constant function. It's just a horizontal line. So as x approaches any number, the y value is going to be constant 6. So we just learned something. The limit as x approaches any number of a constant is simply that constant. So that's going to be 6 plus the limit as x approaches a of f of x is given to me, that's 2. And the limit as x approaches a of g of x is 3. So the answer is 8/3. Pretty simple. All right, let's try the same concept here. And we're going to break this up. So we're going to say the limit as x approaches a of 5 over the limit as x approaches a of 3g of x. I'm going to bring the 3 out in front, and by way of using the constant multiple rule, we just said that the limit as x approaches a of any constant is that constant, so 5. And then we know that the limit as x approaches a of g of x is 3. 3 times 3 is 9. So there is our limit. Pretty simple properties. All right, let's say we do not want to graph a function, or let's say we don't have the strategies for graphing a function, but we still want to evaluate the limit. So whenever we get a 0 over 0 limit, that is once again called an indeterminate form. And what we have to do is we have to figure out another strategy for evaluating that limit. So the first strategy is simply direct substitution. That's not a 0 over 0 limit. That's just plugging the number in and figuring out what the y value is as x is approaching a certain value. So if the function is continuous, such as letter A, this is a parabola. So essentially you can get the limit by just plugging the number in to the function. So if you plug in 1, you will get 1 plus 3, which is 4 minus 5, so negative 1. Chances are you will never see an AP problem that easy. So let's move on to the other types of problems. Let's say part B, you plug in 0, and you get square root of 2 minus, and this should actually be square root of 2 here. So let me fix that. There we go. So if I plug in 0, I get root 2 minus root 2, which is 0 over 0. That is an indeterminate form. Therefore, we need to find another way of evaluating this limit. So this is what's called rationalizing the numerator. It's when you multiply the top and bottom by the conjugate, then substitute. The conjugate is when you change the middle sign between two terms. So we're going to take root 2 plus x minus root 2, and then we're going to multiply that times the conjugate, root 2 plus x plus root 2. And then on the bottom, we're going to do the same thing. We're going to multiply the bottom because we have to do the same thing to the bottom as we did to the top. When we do that, let's see what we have. Root times root. When it's the identical root, it just gets rid of the square root. So that's going to be 2 plus x. Now, the outside and the inside are going to be equal but opposite, so they're going to cancel. So then you have negative root 2 times positive root 2, which is just negative 2. And that is going to result in these two canceling. So that's going to leave you with an x on the top. Here's the key. Do not distribute the x to the terms on the bottom. Reason being is because you want to see them cancel. You want to see these x's cancel. So you do not want to distribute the x on the bottom to the terms on the bottom. When you do all of that, let's move over here. That is simply going to leave you with 1 over square root of 2 plus x plus root 2. Now, my friends, you can determine what the limit as x approaches 0 is. Take the 0, plug it in, and now what you're going to have is 1 over root 2 plus root 2, which is just 2 root 2. So there is the answer to this limit problem. Okay, let's try a couple more examples here. The limit as x approaches 1, you have a rational function, which is nothing more than a function that has x's on the top over a function that has x's on the bottom. When you plug in 1 here, you are going to end up getting, let's see. This should actually be the limit as x approaches negative 1, or the problem won't work. So you plug in negative 1 to the top, you get 2 minus a minus 1, which is 3 minus 3, which is 0. Negative 1 plus 1 is also 0. So we get 0 over 0, we have to find a different method. We're going to use method 2, canceling out like factors. So here's the steps. Factor, cancel, substitute. Factor, cancel, substitute. So let's go ahead and do that. We're going to factor the top. That's going to factor into 2x and x, and looks like minus 3 and plus 1, and that's going to be divided by x plus 1. let's see, did we factor that right? 2x squared, 2x, yes we did. So then the x plus 1s are now going to cancel out. And now we're on step 3, substitute. Plug in your -1 here and you get -5. So once again, you'll get pretty quick at doing these limits after you practiced a few. Now step D. Here you have once again a situation where you're going to have 0 over 0. Plug in 0, you're going to end up getting 0 over 0. Here's where we have to go to the fourth strategy, which is to simplify the function algebraically, then substitute. So let's see what we have here. 1 over x plus 4 minus 1 over 4. All of this divided by x. We've got to get a common denominator between these two fractions. So we're going to multiply top and bottom by 4. And then we're going to multiply this fraction by x plus 4, top and bottom. Now that we do that, we have a common denominator. So we're going to have 4 times 1, which is 4. And then let's take this negative. You got to be careful. This negative has got to distribute to both of these terms. So minus x minus 4. And this is going to be over the common denominator of 4. And then x plus 4. Now this is still divided by x. So I'm going to divide this by x over 1. I'm just going to write the x as x over 1 because in a moment we're going to flip this and multiply. So 4 minus 4 is gone. And now you're left with, let's continue it up here, -x over your common denominator. Now here's the step I'm going to do. Dividing by x is the same as multiplying by 1 over x. Basic strategy of dividing fractions. So then now I'm going to cancel the x's out and rewrite it. -1 over 4, x plus 4. So hopefully you're seeing the process. You always have to get something to cancel. Then your last step is to substitute. So now we're going to substitute 0 in for our limit. And we end up getting -1 over 16. And there's your answer. Okay, now we're going to talk about two very special trig limits. And the first is as x approaches 0, sine of x over x equals 1. And this one is going to be 0. Now, if you want to convince yourself of these, you can graph both of these on your calculator and just look at what's happening as x is getting closer to 0 and look at what the y value is approaching. This one here is the main one that we're going to use. And if you graph it on your calculator, it's going to look something like this. It's going to oscillate, and the bigger x gets, the smaller, the closer the function gets to 0. And you can see that here because if you plug in a really big number like say 10 million on the bottom, that's going to be 10 million. On the top, well, the sine function is always going to be between -1 and 1 because of the way the graph works. So you're going to basically have a very small finite number on the top over a very big number on the bottom, which is going to give you 0. But as x gets closer to 0, the y value gets closer to 1. So let's see how this works on a couple of sample problems here. Letter A, if we plug in 0 into the top and bottom, we're going to get 0 over 0. So we know that that is going to be an indeterminate form, so we have to find a different way of evaluating this limit. So that's going to give us sine of x. And if we factor the bottom, we can take out an x. Now with practice, your eyes will recognize that this is what you can do. And then what you can do is you can break this up into two fractions that are multiplied to each other. All right, and so now that's going to give you the right to use one of the properties of limits. So we can say now as x approaches 0 of the first one, we'll say f of x, times the limit as x approaches 0 of the second function, which we'll call g of x. And so now we can use this property that the limit as x approaches 0 of sine of x over x equals 1. So we can replace this whole thing with 1 times. Now you can plug in 0 in here to this x and evaluate this limit separately, which is going to be 1 over 1. And then multiply the two limits together, and bingo, you've got your limit. Okay, letter B. This one is a little bit different. And so we have to learn how to do this. So the idea here is if you take the limit as x approaches 0 of the sine of anything over that thing, it's always going to equal 1. It could be sine of dog over dog, sine of cat over cat. It doesn't matter. So what you want to do here is you want to try to get this particular situation to occur. So we're going to say 3 sine of 4x over, and I'm going to just put a 4x on the bottom here. Now, if I put a 4x on the bottom here, I have to balance it by putting a 4x on the top. All right, and then we're going to do the same thing to the bottom. I'm going to put sine of 3x over 3x, but I'm going to multiply it by 3x. So let's see if that makes sense to you. If I take this 4x and cancel it with this 4x, I'm still getting 3 sine of 4x, which is what we have on the top. Same thing on the bottom. If I take the 3x and cancel it with this 3x, I get sine of 3x. Now, why did I do that? Because now I can use this property, sine of dog over dog equals 1. So I see that the sine of 4x over 4x, these two things are the same. So that limit's going to be 1 times 3 times 4x. So that's going to be 12x on the top. And then on the bottom, sine of dog over dog, these are the same. So that's going to be 1 times 3x, which is 3x. And then we can cancel off the x's, and we end up getting 4 as our limit. Okay, we've come to the last problem here, and this is another piecewise function. So it splits at x equals 2, so we're going to take 2 and plug it into the linear function. 5 minus 4 is 1, so we have the ordered pair 2, 1. And we're going to take 2 and plug it into the square root function. 2 plus 7 is 9. Square root of 9 is 3. So already we can see that these two functions are not going to connect. But let's go ahead and graph it anyway. So 2, 1, and we're going to put an open circle. And now let's see what this function looks like. It's a linear function with a negative slope, and it is only valid for when x is greater than 2. So x is greater than 2 is going to be all of this to the right, and negative slope means it's going to be going down. So there's our linear function going down with a negative slope, x is greater than 2. Now we have the square root function, and this is going to be shifted left 7. We learned that from pre-cal. So 1, 2, 3, 4, 5, 6, 7. And it's only going to be valid up to the point 2, 3. So it's going to be a square root function. There it is. So now, there's your graph, check mark. Find the limit as x approaches 2 from the positive side. So from the positive side, the limit is approaching or heading towards 1. From the negative side, the limit is heading towards 3. What can I say about the limit as x approaches 2? It does not exist because, and you have to write all this out, the limit as x approaches 2 from the left of f of x does not equal the limit as x approaches 2 from the right. And anytime you have those two limits that are not equal from the left and right, the overall limit does not exist.